Hey everyone, so today we are deriving formulae for the geometric sum Sn and the feature value annuity formula Fv. So we'll start immediately after this. So to do this, we need the series. So the geometric series looks like this. Sn equals to A plus AR plus AR squared plus some other terms in here, and then until we get to AR to the n minus 3, AR to the n minus 2, and AR to the n minus 1. So looking at this series, you should by now know how it works. That this is the first term of the sequence, A, and R is the constant ratio that we multiply each term to get the next one. So we multiply this one by R to get this one, and we multiply this one by R to get this one, up until here. So this one is the nth term in the sequence. So there are n terms in this sequence or in this series. Now we are going to use this and multiply it by R to get R as n, which gives us AR multiplied by AR squared plus AR cubed plus all the other terms as well, until we get to this one here, where we have this one, the exponent has been added by 1, just like every other term. The r's have increased because we multiplied by r each and every term. So it means this one, when you add 1, you get this one. Multiply this one by r, you get this one. Multiply this one by r, and you get this one. So this will be the last term. So we still have the same number of terms. It's still n terms. So the two sequences have the same number of terms, the two series. So now, to continue with our derivation, we're going to subtract the two equations. So on the left hand, to subtract them, you'll see we can align them. You see that this one is aligned with this one. They're the same. This one is aligned with this one. And again, we have another term here. That is AR to the power 3, which is aligned with this one, and all the other terms in between will align as well, just like this, up until we come to the last 3. This one will align with the one just before this one, and this one is aligned with this one, and this one with this one, but this one does not have any like term in the first equation, just like A here doesn't have a like term in the second equation. So when we subtract the two equations, so we'll be left with A, and these will minus out. All these other terms in the middle will minus because they are the same, up until we have negative AR to the exponent n. Then we can take out common factor both sides. This side we have Sn as a common factor, this side we have A as a common factor, so we will get this. Then to remain with Sn, we will divide both sides by 1 minus r, and that is the formula that we have been trying to derive. So that is the formula for Sn. And if we multiply the numerator and the denominator with -1, we can also write it like this. So these are the two forms that it can take, but they're the same and they do this exactly same job. Okay, Now next, after this, now we go and try and derive the future value formula, the future value annuity formula. And we start by saying we have a timeline, and our timeline starts at T0 and it goes all the way up until Tn. So this is indicating all the number of periods that our annuity is going to be observed. So we have n periods. There are n number of periods here. The periods could be years, the periods could be months, whatever. So, but in general, we say these are periods. And we're going to have an annuity. So an annuity, somebody deposits some money, the same amount of money each and every month. So in this case, we'll say the person is depositing X every month or every year, whatever it could be. So each period, there is a payment of X that has been made. And all these payments, we want to know what their value is at the end of the n periods. Now, I want you to notice something. This first, or the very last payment is going to be in the account only for a second because it's not going to earn interest. So the day we deposit the last payment is the day we are going to check how much is in the value in the account. So this one will not have moved or charged any interest. Now this one here will only bear interest on one period from here to here, and this one will bear interest for the two periods from here to here. Now what I want you to see is that this very first payment here, you would think that it is going to be in the account for n number of periods, but it is actually n minus 1. If the payment was here, yes, it would have been n number of periods. So because it's here, the first payment is going to be in the account for n minus 1 number of periods. All right, so now that we've understood that, let's talk about, we say the interest is I, and then we are now going to look for the sum of all these monies and they are earning interest. So we have FV that will be equal to x plus 1 plus I, x multiplied by n1 plus I to the exponent n minus 1. So this is this value here. So it has moved from here n minus 1 number of periods. So that means we have n minus 1 here as the exponent. The second one will have moved only n minus 2 number of periods. So this one here is this one here. Moving from here to the end, it's n minus 2 periods. And this one again will be n minus 3. Then we'll have all these other ones moving just the same way. And then we then come to this one, the one that's going to be in the account for 2 periods. So it will be x multiplied by n minus 1 squared. And this one here, it moves only one period, which means it will have only 1 plus I multiplied by it. And the very last one is the one that we talked about that doesn't bear any interest, so it's just going to be x. Now, I want to rearrange these terms so that they are in a form of a geometric pattern. It is a geometric pattern, but I wanted starting with the x. So let's put them like this. Now we see that this looks like a geometric pattern. So this is the first term of our sequence. and this is the first term multiplied by an r, which is the bracket. So this is the constant ratio in our series. As you can see here, we have 1 plus r, 1 plus I to the exponent 2, and then we'll have another 1 to the exponent 3, and so on up until the very end. The last one will be x multiplied by 1 plus I to the exponent n minus 1. So it's clear that we still have n terms, so which means we can use Sn formula, which we just derived in the previous derivation. And that formula says a multiplied by, so I've taken the second version that I've shown you in the derivation. So now we need to identify what our a is going to be, what our r is going to be, so that we can see what this is going to end up as. So our a is the first term, that's x, and our r is the bracket 1 plus I. So we'll substitute that in. So we say a is our x here, and we have our r, which is 1 plus I to the exponent n inside the bracket, just like in the Sn formula, minus 1 over our r minus 1 again in the bottom, the denominator. Now we see that the ones will minus each other out, and hence we will get our formula for Fn, which is x, the payment, multiplied by 1 plus I to the exponent n minus 1 in the numerator divided by I. So that is how the formula. Thank you very much for watching up until this far. Like and subscribe, and I'll see you in the next one.